All right, you can go.
Great. Thank you for the invitation. My name is Yen Tinling. I'm currently a staff scientist at Information Sciences Group, CCS3, at Los Alamos National Laboratory. And so this is a collaborative work with Javier Santos, Zach Fox, my former postdoc, currently at Oak Ridge National Laboratory, my colleague Nick Albers. And we're supported by internal programmatic funding by laboratory-directed research and development. So here is a quick outline of today's talk. So I'll give an intro and quick review of continuous state generative diffusion model. And since we're all, in some sense, experts in this, I'll skip the typical, very plain intro, but trying to give a sort of our perspective kind of intro and identify what we see that's missing in the current technology or landscape. I'll present to you the core research questions that we had when we were trying to understand what diffusion models are. And then I'll present you generative modeling discrete state spaces that comes with a general theoretical foundation and also the spatial example, which we call Blackout diffusion. And then I'll answer the research question in conclusion. And so for the record, this is a science paper, so it's less of an engineering that we're trying to beat the state of the art, but more on providing understanding of the these type of generative diffusion models. And so it should be a very short presentation, and so do feel free to interrupt if there's any question. It's more interesting to have a discussion than a monologue.
I really appreciate maybe I can interrupt at the start.
Yeah.
It's what we always say when we always talk about our research, especially what we're doing with Gabriel now. We talk about our research about diffusion model, that we are doing science, and our object of study is the diffusion model itself, which is not a physical model, but we study it as if we're doing physics. And I think it's very cool to also that you also see that this way, because I think it's a very promising line of investigation.
Thank you. Yeah. I'm glad that you think the same. So here is a short outline. So this is going to be the introduction. And since we're all the experts here, so there are two formulations of continuous state diffusion model. And I'm going to specify continuous state because both of them relies on Ito process or Gaussian diffusion. And so the first sort of the first version of it is the discrete time formulation. The first paper on it is should be 2015, so it takes time, but Ho et al. Actually proposes the noising diffusion probabilistic model. Somehow was probably the first paper which ignited the entire field. Right? So that's 2020. And the idea there is that you're using discrete time Markov chain but in the continuous state to noisify the image here. I hope you can see my mouth. So the image was actually noisified using the forward process, unfortunately going to the left using the schematic diagram. And you ask the neural net to actually learn how to go back using conditional formula. The second formulation is the continuous time formulation. That's Ho et al. Using score-based generative modeling through stochastic differential equation. So then the idea here is that now instead of it having the discrete time transformation, you're thinking this on the continuous time domain, and you have a 4SDE which noisify, unfortunately, left to right now, not the same as here, somehow opposite. And then in the reverse, there existed a reverse SDE, which goes from the noise to data, and the neural net actually tried to learn the score function. So our take here is that if you observe the theory end of this, the key construct here is so coming from, for example, mathematical finance folks or stochastic processes, the whole idea here is that there is a Brownian bridge like calculation here, that you're trying to compute the conditional mean and variance given later time and initial, you try to compute the one step ahead, one step before, sort of in the forward to the left, backward to the right sense. Right? So that is how your learning target. Now, if you go through the derivation, it's quite special to Gaussian diffusion distributions. So without a Gaussian distribution, we can't do that. Now, for continuous sign formulation, the first thing that we had a problem, like I'm sort of pedantic in the sense that coming from stochastic processes, and that this title is in some sense too general. There are many stochastic differential equations, and there is a subtitle Ito stochastic differential equation. So the whole sort of setup here is actually Ito. So these are the physical diffusion process, which has to live on the continuous domain, and the fundamental noise is actually a Gaussian, and that's what we know. Now, the reverse SD formulation there was based on Anderson et al. Sorry, Anderson 82, which is applicable only to Ito SD. If you read through that paper, it's quite clear. It's based on the Wiener process. Cool. So this is sort of on a continuous state diffusion model. It's actually a theory, and in my opinion, things are quite completed, right? So the rest is actually engineering problem, which is also important in some sense. But the theory end is not like I don't see an empty space that we can make contribution. So our motivation and research questions there is the following sort of 5 outstanding questions. The first thing is Gaussianality. So most of these kind of exist in diffusion models, and we had to focus on most of it. They're like scattered, very single isolated ones which do not depend on Ito processes. But here, the Ito process is formally defined as a diffusion in the physics sense, and also in the mathematical sense. So basically, you can describe the probability distribution by Fokker-Planck equation. Or if you write down the SDE formulation, it's actually the fundamental noise there is Wiener. And you use that to noisify the data. And the first question we ask is whether or not we can find other processes, right? So is Ito that special, right? Based on the derivation there, it seems to be very special because a lot of Gaussian properties that we use to derive the learning target. The second question is, so Zach and I, my former postdoc, we were working on many research problems that involves discrete data sets. So we're looking at, for example, single cell, single molecule, gene expression data, which are fundamentally discrete. They can be 1, 2, 3, 4, 5, up to 50, for example, but they have to be discrete. Now, the other domain that we're working on is graph models, and the edge can be either there or not there. It has to be sort of binary. So we are not very satisfied. I mean, you can say we're a little bit OCD in the theory sense that there are ad hoc ways where you say, well, it's data is discrete, let's make it continuous first. And then we apply continuous state diffusion models after we do, perform inference, it's going to be on the continuous domain, let's discretize it again. We're not really happy with that approach, and we're thinking, is there a way that we can somehow preserve these kind of a discreteness property throughout the entire sort of technology? The third thing that's most interesting to us is that there is this outstanding notion that that diffusion model is actually first you noisify the data, and then you try to train the neural net to learn how to denoise in the reverse time direction. And so somehow the intuition there is there, but we're wondering that whether or not that's the right way to really understand the generative diffusion model. So we'll see. Now, the fourth is sort of a minor technical point, is that there are some hidden annotation that the terminal distribution of XT is similar to latent space in autoencoder. And Luca, you work on variational autoencoder, you know, there is a certain kind of latent sort of annotation, information bottleneck. And then we can somehow probably learn some structure in the latent, that's sort of the idea. Now, we can only say there is these kind of annotation. Theoretically, no one really said that. But for example, if you look at Song et al., they constructed something called probability flow method, which, by the way, is a very old method in plasma physics. It's a way to actually bypass running Euler Maruyama. But in order to doing so, you somehow have this annotation that your terminal distribution looks like a latent space. Now, we were wondering whether or not it's the right way, and we want to show that it's probably not the best way to understand this, and we want to create one specific example to show this. Now, the reverse time process, the theoretical question that we really want to ask is for Ito processes, the complete mathematical theory by Anderson. Already tell you everything, right? And so, so for Ito processes, it's there. But what if we want to bypass the Gaussianality and say we go to a different kind of stochastic process, and what's that reverse time process? Sort of a theoretical question we ask. So the proposition here is simple. There are so for all stochastic processes, you can always decompose it into two types. One is a diffusion, the other is a jump. And so since the diffusion is taken care of, let's just look at the jump. And so the simplest way of looking at jump processes is to go to a discrete state. So here we either construct a discrete time or a continuous time, but both of them have to be discrete state Markov process. Now, for any stochastic processes, there are two formulations that we can formulate the process, right? So one is to describe the evolution of a distribution. And so the evolution of a distribution here now follows a master equation. And so that's usually how we learn. And so for the rest of the talk, I'm going to focus on the continuous time formulation. And there is a corresponding discrete time formulation that's sort of easier. So we will, the details are in the paper, so I'll just skip that. But for a continuous time, basically you write down the master equation, describe how the probability of a specific state is how it evolves, right? And you write down the master equation, and then there you have a Markov process. So this is a Markov transition matrix. Now, in the typical SDE form, that it goes back to our sort of objection to the previous Song et al. Paper. There exists an SDE formulation for jump processes, and when you write it down, it's actually somewhat similar to your typical SDE, where typical SDE you write down the D Wiener process, standard Wiener, but here is a standard compound Poisson process, right? So because things jump between 0 and 1, so that's a fundamental noise there. And so formulating the forward process to noisify the data is straightforward. It's very easy. The key question here is, now in the reverse, what's the reverse time process? And what's the score function? Like, the key idea here is to learn this score function for the Gaussian diffusion process. But what is a score function in the discrete state spaces that we just do not know? So what is the learning target? Like throwing this problem to neural nets. How do we write down the learning target and the loss function, etc.? So this actually, by doing so, we address all of the questions, right? So now for Gaussianality, apparently here we're using Poisson, so there's no Gaussianality. Now, there is an intrinsic discreteness of the system. You'll see that we'll be able to address noisifying and denoising using a specific process, and as well as the latent space question. And then we want to build the reverse time process here, right? And then the overreaching goal here is now consider all the Markov stochastic processes. So you have Anderson et al. Anderson 82, which gives you the reverse, and we want to construct the jump, the reverse for the jump. And now you have both of the formula. Now you can play the game with describing a lot of processes, like all the stochastic processes here. But then the first question is, does it work? So this paper is really to show that this can work. I'll show the highlight of the derivation. It's a little bit pedantic, but I want to at least sort of outline sort of the idea there. It's in Appendix A. sort of the key results here. But I'll in the next slide, I'll try to present a more physicsy sort of intuitive way to understand these. So these are formal algebraic operator algebra. So it's all algebraic manipulation. So the conditional probability distribution is defined as this. So you basically like propagating time s, state n, to time t, state n. And we denote that as a sort of shorthand notation. We know from stochastic processes, and this is 1930 technology, right? So it's we can write down the Kolmogorov-4 equation, which describe how this sort of the MT evolve forward in time. Right? So this is the typical forward Markov Chapman-Kolmogorov equation you write down. Now there is a backward equation, and the backward is you condition on, not condition, you give it the terminal state L and T there, and now you want to see how the previous state M and S somehow go back. And so in mathematical finance, this is related to, for example, Feynman-Katz formula, and you also use these kind of formulation to compute, for example, hitting probability, first passage time, etc. So this is a backward equation. One of the errors that we found in the literature is in the very beginning, so Stein citing Feller only talking about the backward equation, and the backward equation is not what we call the reverse time process. So specifically, the reverse time process is actually you condition on the initial and some terminal condition, and then you want to go a little bit back. So your t is a little bit later than s, and you want to describe how this probability distribution evolve. So ms. So then it's simple conditionals, and so you can actually write down the conditionals, and in the end, what you found is that you have two terms. One is described by the forward, and the other would be described by the backward. So then the DDS, you apply the DDS on this probability, this different side here. Now you use chain rule. Now you have a forward, you have a backward, and then you do awesome calculations. There are some technical details. You have to express the Markov transition matrix as a combination of discrete state jump operators. And then there are some operator identities that you apply, but it's very straightforward, very tedious, but very straightforward. And in the end, what you will get is something that is very similar to the Ito process. So in the Ito, let me remind you, in Ito, we have a forward process. Right now is a Ito SDE. And the reverse is also a Ito SDE. It's proven by Anderson. Now, the key insight there is that there is a term which is the Stein score function of a forward solution. So you need to know the forward solution, and then you plug the forward solution, and that term tells you how to do anti-diffusion, right? So in the forward sense, your diffusion, you lose information, things go away from your mode. Now, this term basically tells you how you would actually revert that using the drift. And so knowing the Stein score function tells you how to do that. Now, for the jump process, as it turned out, in a normal form, nomenclature here, we have a forward process writing down as a master equation. As it turned out, the reverse time process is also a master equation. This master equation for each of the jump rate from I to j turned out to be the jump rate of j to I, and you have to know the forward solution there. And then so somehow it's as simple as that. Out of the very tedious calculation, this is the solution. Very simple. It's even intuitive if you look at this. And now the key idea here is the same. You have a forward solution there, and this plays a role of the Stein score there. And then you have a forward transition rate, but now you swap it. So using a graphical graph model, right? So if we have 5 states, and suppose I design a Markov chain, or even a continuous time, either continuous time or discrete time Markov chain. Here is a continuous time, where I will say there is a transition rate from 3 to 5. So here is 3 to 5, there's transition rate. And suppose that's the for process. The theory tells you that in the reverse process, all the directed jumps was reverted. And that's sort of intuitive, right? So if you can jump from 1 to 3, now the reverse process has to be only from 3 to 1, right? And the more important thing there is the rate there. So the reverse rate denoted by this tilde will be, so the 5 to 3 would be the for rate, and then with weighted by the xt is equal to 3. So the probability of the state at 3 at time t divided by the probability of a state at 5 at time t. So this can be understood by even heuristic physical argument of the forward-backward probability flux, right? So if you think about the flux, right, we're looking at things, how the probability is moving from 3 to 5. And the probability flux there is nothing more than P3 times M53, right? Now going backward, that probability flux has to be equal, right? So it's like I rewind if I somehow record this physical process, and then I quantify the probability flux, and then after I record it, I play it backward. The probability flux is nothing more than going, it should be, this magnitude should be the same, but now it's, in order to formulate this, I have to formulate it as a 5 to 3 times a p of the probability at here, right? And so now you equate it, immediately you get this. It's one way, sort of a more physicsy way of understanding, and also very easy to remember the formula. It can be also established by applying conditional base. So in our paper, we basically, but there's a extremely hand-waving argument. You basically go from 2 time, so one previous time at 3, one later time at 5, and then you play the conditional base, and then in the end of the day, you say, let's send the times, the delta t down to 0. And that's one way, another way to understand that.
Which, by the way, it's also hand-wavely how you prove Henderson theorem. You just look at the moment, all the moments of the distribution vanish except for the first 2, and then you can prove that the transition is Gaussian.
So here it's Poisson.
Yeah, but
so
but the same trick will work.
Yes, looking at the moments can also work, definitely. So there is a technical detail I want to at least touch upon. So the idea here is then you have a discrete state and you have a continuous state, and then you go back to the entire stochastic sort of a theory there. You start to think about sort of a connection between them, right? So there is also 1930 technology in statistical physics called Kremers-Moyal expansion. So it's a formal asymptotic expansion. So basically in the dense limit, if your discrete state space is in some order states. So if, for example, if you think about a real line, I can discretize it first, and then I can make it denser and denser, and I can design the jump process on the discrete domain, and then send the density to infinite. And in that asymptotic expansion, you would hope that whatever you obtain is similar to the continuous Ito process. And the technology there is Kremers-Moyal expansion. And so what we show in the appendix, which we never used in performing any machine learning task, but it's just fun to do it and to understand this, is that you can have a forward discrete, and then you can do the dense limit of Kremers-Moyal expansion. And then there's a forward Ito. Now you use Anderson 82, you go to the reverse Ito. Then the question is, now we describe how the forward discrete, using our sort of theoretically constructed reverse discrete, if you do the same dense limit, would they converge to the reverse Ito. And the short answer is yes. After several pages of calculation, it did converge. And then for theoretician, that means somehow you're happy, right? So the universe is complete again. No sort of a strange exchange of limits, etc. But basically, we can consider that this is it's a whole sort of a picture there, right? So now things are nice in some sense. Now then, so I'm jumping to the next topic, sort of a more numerical side of things, and to convince the community that this can be useful. More than the theoretical sense, we kind of have to construct the process and show that this can learn, right? And so the process here, we look at imagery data, and so each of the channel there, it's kind of, even if you think about it, for imagery data, digital imagery, images, they are actually most natural to apply this technology, because the pixel, each pixel or each channel is actually naturally discretized from 0 to 255, right? So in the 8-bit image, that is. So then you'll say, well, let's consider the following process. It's the one of the simplest process that we learn in stochastic processes 101, is a pure depth process. Pure depth process means that suppose originally that channel has 255, it can only go to 254. If it has 3, it can only go to 2. If it has 1, it can only go to 0, sort of nearby. So you just decrease 1 unit of the intensity. Right? Now, and you note that by doing so, your x is equal to 0. Everything go to x is equal to 0 if you wait long enough. And another detail is that the transition rate is proportional to the current state. So 255 goes to 254 with transition rate n. And you, by doing so, you somehow think of each of the intensities like an independent unit. They just die with a unit rate 1. Right? And so part of the reason of doing this is, well, A, analytically it's simple. B, we can justify to our LDRD that we are doing something that's related to, in some sense, it's a radioactive decay process, right? So it's one of the processes that Leno knows for a long time, right? So it's a stochastic process describing how for example, how beta decay goes. It's well studied. So the forward solution is a simple binomial, but the rate there depends on the time. There exists actually a bridge formulation, which out of our surprise, we couldn't find it in the literature. So it's not Brownian, it's binomial. So we call it a binomial bridge. And there is a very nice physical intuition that next time when I teach a stochastic process 101 is going to be in the final exam, and ask a student to solve it. You can actually solve it by generating functions, but there is a very neat trick that by even arguing in the physicsy sense, like Feynman used to do, you basically can come up with this expression without doing any algebra. So that's also very nice. And so this can be performed for arbitrary SNT. So then it's a finite time jump. So it looks like a DDPN like learning. And so the connection there is in DDPN, you do Gaussian. And so this Brownian bridge kind of formula. And here we have this binomial bridge formula, which we can use to learn. And the reverse time transition rate can also be derived. So this would be analogous to the learning the SDE. So here is an instantaneous transition rate. And so at any given point of a time, we will come up with an expression there, and it's very simple there. And so you basically ask a neural net to either learn this or that, and we did both, and their performance are roughly the same. So to give intuition what's going on here, right? And so here is a simple process that we just say, suppose the state is 0 to 8 and 9 discrete states, and start from 8, the maximum, For Gaussian, you basically perform a Gaussian Ito process, and then you converge to the mean around 4, and the terminal time distribution here. So here, left-hand side is a 4, and the right-hand side is a reverse time process. And the terminal time here is set so that this distribution can be approximately the limiting distribution of this process. For Blackout, everything goes down. So if you start from 8, it goes to 7 at some random time, and goes to 6 at some random time, and then it all the way goes down to 0, and it stops there. And for the reverse, you start from 0, and then it goes up. So that's the sort of the intuition there. Now, the key intuition here is that for Gaussian, you always, in the forward pass, because of the design of that process, the variance always is a monotonically increasing function. So the variance here, the noise, is getting larger and larger. For Blackout diffusion, things are like weird, right? So you see some spread here. So for example, at this time is a maximum variance there. And so you inject noise first, but then later you denoise even in the forward pass, and then you converge to you absorb to a singular distribution, a delta distribution at 0. And so this is for each of the channels. And so for each of a pixel, each of the color channel, you perform this, right? So the sort of applying it onto an image, this is what you see in Gaussian. So in the end of the day, you have some isotropic Gaussian for each of the channels. Now for Blackout, for all of them, they go to sort of a black, right? So that's why we call it a Blackout. Formally, it's a jump process, but we still call it diffusion, so that we can fit into the diffusion model. And on the other hand, you can also go back and to this figure, you realize that even jump process on the graph, we have graph diffusion, right? So in some sense, we are, in some sense, also a diffusion, but not in the typical sort of a physical diffusion sense. It's a generalized diffusion. So fundamental noise here is Poisson. Limiting distribution is singular, or black. The forward process injects noise and removes the noise after a specific time. You can even analytically calculate it. The reverse does exactly the opposite. You have to first noisify and then denoise. Now, the path's realization of a process is constrained naturally on the discrete space, sort of addressing our issue that we want it to be intrinsically discrete, right? And the other thing is the bounds of the system is actually respected, right? So if I have 0 to 8, here in the Gaussian, you can see that sometimes it goes out between the 0 and the 8, and we somehow, yeah, it's not a big problem, but it's like, again, theoretical OCDs, it feels weird. There's a technical detail that we identify is that the noise schedule, as all the diffusion models, it's super important, and I think it's a really underexplored area. We frame it as an optimal experiment design problem. So basically, you have this continuous time process, and now the question you want to ask is, where is the best time that I put my neural net and I'll say to learn? And so we have handled some of these kind of problem in the sort of experimental design domain, and somehow we try to frame it as this problem. And we came up with a very heuristic approach, which we rely on Fisher information of a forward process. I should say this is not theoretically sound, but it gives you one answer, and it's no worse than let's put in a cosine schedule, let's put in a linear schedule, but somehow when we put in, of course, the process is not the same as the Gaussian diffusion, so most of the Gaussian diffusion noise scheduler doesn't work. They don't work. So we have to come up with something new. And this somehow gives us a nice analytic formula, which looks intelligent. We're still pondering that whether or not it's really intelligent or probably another just heuristic type of not really that sound. So, but it gives you a formula. We follow this formula, and then we design the noise schedule. Some fine prints here before I show you the sort of very simple results, very concise. So for learning, we talk about we can do either DDPM type of a finite time formulation. There you learn how to do this binomial bridge. Ask a neural net to do this. Now, the instantaneous formulation is similar to the score matching methods. You learn the reverse time transition rate. So that's instantaneous. So at any given point in time, it doesn't require 2 times. It's instantaneous time. Now, if you're familiar with score matching, they either apply L1 loss or L2 loss, which is another thing that we're not completely happy. That doesn't seem to be a theoretical foundation why L1 or L2. And if you really go drill it down, you realize that there is a pre-weight, the weight for each of the time that you have to do. So for our case, we basically have the entire probability distribution. We just use the maximum likelihood approach. So we didn't do the ad hoc sort of temporal weights. Everything just follow the math. It's a MLE. For generating samples, there are also 2 ways. We can do finite time generation. It's similar to DDPM. You basically just use the...
I didn't understand. So what kind of loss are you actually using for
so the loss there, so let me quickly jump to, I didn't put it here because it's too nerdy. Oh. So here is a negative log likelihood. It's an instantaneous log like, so you have Poisson rates there. So this is what your neural net predicts. And then there is what you computed using the theoretical reverse time rates. Right? And then so now for Poisson, what you can do is you send delta t down to 0. And this can be shown to be the exact negative log likelihood. And so you do the delta t expansion and sending delta t down to 0. In the end of the day, you got into some weird, not really weird, but some formulation like this, and it's in continuous time, so you integrate over the time. Okay. Now there is a noise scheduler there, so the noise scheduler effectively put in the weights there. So that's the idea.
That's interesting. That's also interesting. Again, we seem to think it the same way. I was when I was thinking recently about this, the theory is mostly complete, except for these things that we kind of accept this L2 loss as if it's kind of from the Bible or something, but there is not a very specific theoretical reason why that should be optimal in most situations. And it's true that it gives us a very clean loss, the clean denoising autoencoder loss, but still, it's a kind of a gap in the theory that people are just accepting.
Correct. It's very interesting. We're actually also looking into this. So as a matter of fact, you can do asymptotic expansion of this. And in the local, say at the MLE, you do expansion, and it's a little bit like typical sort of expansion of any potential minima. You get the quadratic, right? Now, the funny thing is that quadratic is not the L2 that people are using. So somehow the L2 loss there, our hope is actually like putting in some theoretical foundation, and then all of a sudden our performance will be like several orders of magnitude better. But apparently that doesn't work, right?
Well, I mean, I would say there is a reason for using the L2 loss, is that you get a very clean denoising autoencoder training.
Yeah, but what I'm saying, there is a connection. Even from this MLE, you can construct the L2, but that L2 doesn't give you satisfactory results. The weight is not the same as what people are using nowadays. So yeah. So locally you can expand any minima as a quadratic approximation, and that's what optimization theory usually we use that, right? And also in application. So the aim we tried to try to do that, and then put in like the correct expansion, but somehow it just doesn't optimize. That's the sort of theory versus reality. So for generating sample, we have also two ways. One is a finite time generation. You use this bridge formula. You basically hop backward a finite time, right? And then the second way of doing this is we can actually instantaneous. So it's somewhat you have a SDE, now you have to integrate backward, and then now you have to discretize a time step in the Gaussian setting, Ito setting. You use Euler-Maruyama. That's what most people use. In the corresponding Euler-Maruyama for jump processes, it is called tau leaping, and so that's what we do. And so the fundamental statistics here, if you're using the first one, is going to be a binomial random variable. If you're using the second, it's going to be a Poisson random variable. Both of them give you roughly the same behavior. We tested on binarized MNIST, the Cipher 10, and Celeb A 64, and they just work. So I should also add, we didn't do a lot of engineering. We just take one of a neural net from the ScoreNet people, and we apply that to our theoretical formulation without fine-tuning. The entire setting of the neural network was the same as when they used it to model Gaussian. So here gives you sort of a little bit animation of how it looks like in the reverse time. So we start from all black, and so left is the binarized MNIST data set, or the right is the Celeb A. So this is how you see. Initially, you generate some, you inject entropy, right? So things got noisified, and to a certain point, you don't even know what things is, what the generated images are. And somehow the neural net saw these kind of discrete scattered pixels, and then somehow it's padding the missing part and gives you the final results. We computed the FID, the inception score, just to sort of check the box, because every paper has this, and we saw that it's comparable to the continuous. It's slightly worse, but we didn't optimize it. So
just to be sure, in the case of the RGB, so each channel can basically either die or be preserved, right? So it can either be set to 0. And once it's set to 0, it will stay to 0.
Yes. So that's a forward process. And in the reverse, you only hop one step up. So inject one intensity up.
Oh, so okay. Yeah.
So the forward you decays, right? And you only go to the decay process. And in the reverse, it's a pure birth process. It's very interesting.
Yeah.
Now, so this is the last slide. I want to wrap back and discuss the research questions, right? So research question, the first is a Gaussian anality, right? So the first thing is fundamentally we use a Poisson noise. So it shows basically that Gaussian noise is not special to generative diffusion modeling. And so now the diffusion, we have to interpret it in the general sense. It's a jump process. Now, Poisson is actually ubiquitous in discrete states acid processes. So our proposed formulation probably supplements the existing Gaussian diffusion model. And somehow it suppose you really want to do things in the discrete domain, maybe it's a candidate that one can try. Now, without doubt that we preserve end-to-end intrinsic discreteness. Now, there's this noisifying, denoising idea, and for this special case of blackout diffusion, I hope that I convinced you that the typical way of thinking that the neural net is learning how to denoise only probably is not the best notion. That at least for this process, the neural net learns also how to noisify the black image initially and generate seeds for generating the final image. I think the latent space issue is quite a done deal. There contrasts to common belief, right? So you have a singular delta distribution which cannot contain any information. So you cannot treat that as a latent space. And the funny thing here is you asked, and then, for example, if we're doing the probability flow, I want to say it's these kind of a singular absorbing state is not special to discrete state spaces. We did this only because it's simple. It's simple to induce this. We push everything down to 0. It's easy to do it in the discrete state spaces. In continuous state spaces, if you have multiplicative noise, you could also have this phenomena. And Feller actually has there's a famous Feller test. Feller has an obsession on this problem, right? So you basically ask, like, you have Brownian particles, and then there is a boundary. Maybe you will be sucked to the boundary and stay there forever. In order to do that in continuous state spaces, you have to have special noise structure. So in continuous state, you also have that. Then you ask the following question: then what happened if you apply the reverse formula or the probability flow ODE to that? And then you realize that the entire probability flow ODE formulation is not amenable to that kind of processes. So you'll enter to a singular distribution there, and then so you will, in the derivation, there will be a 1 divided by 0 or 1, and some infinite somehow just comes out. So
because that requires invertibility. In this case, invertibility will be broken.
Correct. So then, so how to interpret probability ODE is interesting.
No, they're quite fascinating the way they develop. Also, in our symmetry breaking work, you see that the symmetry breaking shows up in extremely different way from the deterministic and the stochastic dynamic. In the stochastic case, before of the symmetry breaking, you have a mean reversion process. In the deterministic case, you have simply 0 score. So the score vanishes before of the symmetry breaking, and then it starts moving.
Got it. So definitely we need to make that talk happen. I want to learn more. Then the final 2 points, I hope I convinced you that there is a formal way that we derive a reverse time process generator, and the result is even physically intuitive. And it's somehow analogous to Anderson's theory for Gaussian interprocesses. Now, the generality here is really what we think there might be a potential. That it implies that formally, you write down any Markov process, stochastic process. It can be drift, it can be jump, or it can be jump and there are plenty types. And so it formally opens a door that you can start to design the processes, and basically you can have the same sort of generative diffusion model in the reverse pass, and then you can ask a neural net to learn it. And so in some sense, like, if we want to be like really creating the hype, we should say like any Markov stochastic process you can do these kind of generative quote unquote diffusion model. So in some sense, we shouldn't even like call it a GDM, right? So it should be, I don't know how to call it, right? Generative Markov model or something, but it's basically generative modeling. And to that, thank you for your invitation, and thank you for your attention.
Thank you very much. It was a beautiful presentation. I think it's